Hello there guys. So it has been a while, hasn't it? 3 years, I think, close to 3 years at least, since I made one of these videos last. I think the last time I made one I was in university, just finishing up, about to move to Amazon, move back to Amazon after my final year. I've been there now for, well, I had been there for close to 2 years, not actually 2 years sadly, when I took an offer with a company called techexUK. They're a UK company based in Bracknell, dealing with video over IP and consultancy for it, and reselling certain software, hardware for specific broadcasters and different companies. And so techexUK also have their own kind of range of software internally: Edge, Core, and Play. MW Core, MW Edge, MW Play, and we do some interesting stuff. But they brought me on board as one of their network engineers, a bit of a network specialist in the team, because it's a relatively small team and they don't have someone who can be dedicated towards the networking side of things. So as part of that, though, I've been asked to kind of try and help the team get up to scratch on some of the topics that I have a little bit more knowledge on. So I took the perfect opportunities to start off very strongly with BGP. And for those who don't know me, I used to work with Amazon in the Internet Edge space in the operations team. And for those who know networking, the Internet Edge space basically uses BGP all over the place. It runs on BGP, and the internet runs on BGP, as I'm just about to discuss. So for those of you who don't know anything about networking and don't care, this definitely isn't the video for you. For those of you who are just starting in networking and are interested in BGP, this talk will give you some real good base knowledge into BGP, I would say. It's a good presentation. I'm pretty proud of what I produced, and it should get you started. For those who are pros with BGP, then maybe it's less useful for you guys, but otherwise it maybe is a nice refresher. Hopefully everything that I say is accurate, but if you feel like I've said something and you're not too sure on it, then feel free to ask questions below. Leave a comment, give me feedback, give me ideas for any of the talks that I can be doing for them. The team internally are very technical, but they don't have too much networking experience, so the idea of the talks is to give them the context, maybe not the actual full technical detail, but the context to understand when I say, let's say, BGP, they know what I'm talking about, for example. So, yeah, and for those who are potentially watching this from techexUK, I've done my best to try and maintain the privacy of the people who were in that meeting when I was doing the presentation. I've removed their names and I've edited off the start and the end. So in theory, there shouldn't be too much from my teammates. But yeah, so enjoy the video. Hopefully it's useful, and hopefully there's more of them coming along. Cool. Thank you very much for watching, guys, and I'll talk to you soon.
Awesome. Bye. So, hey guys, bit of an introduction into BGP today. It was a topic that James suggested I start for a bit of a series on different networking talks. So this is probably one of the best topics that I have knowledge in. Obviously, on a day-to-day basis, we aren't ever really going to deal with BGP and managing it or implementing it, but I think when it comes to wider discussions, and certainly when we talk about the internet, it's nice to have an understanding of what makes things tick and potentially where we can use these things. It also helps, so if you're talking with someone and they mention BGP, we can know to a certain degree, okay, what it actually means. So I guess to start off with, be used for. Obviously, we have the huge use case of the internet, the wider internet as we know it, the public internet. And obviously, the internet is made up of just interconnections between companies at different levels. You've got what we call transit providers, which provide like a full peering table, full internet table with all of the routes on the internet. So an example of what that looks like right now is about 840,000 prefixes on the internet right now. Now, obviously, that'll be a bit smaller if you actually receive a full internet table, because some of them do get summarized, but still kind of shows you the immense scale that we're working at with the internet. And you also have the likes of peers. They advertise a reduced internet table, and usually that'll be something along the lines of their customers' routes or their routes themselves. So you got those two kind of different peers on the internet, and the reason why we use BGP on the internet and why it was basically the first use case is because BGP is very good at dealing with reliability and dealing with unstable networks per se. It's also good at reducing the size of the actual updates and prefixes, and also it reduces the amount of overhead in bandwidth that we need to use on the relevant peering links. So if you think in comparison to OSPF, if we had 840,000 prefixes with inside an OSPF domain, all of that detail would have to be included with inside a LSDB. You'd have to contain all of the details of the relevant links between all the different peers to gain an understanding of the overall OSPF network at a very high level there. Whereas in comparison, BGP only really knows at one time its local neighbors, its peers, and the routes that they're advertising. And it uses certain path attributes and certain attributes about the specific prefixes to make those decisions. So when it comes to dealing with the internet and a wider scale, hundreds of different peerings, BGP can be good at managing that and reducing the kind of churn and CPU load, because it's reducing the communications that you have there that you need to make it work. We can also use it for site-to-site communication with inside a company. So there's two modes of BGP. There's an iBGP, an internal BGP, and an external version of that as well. We'll get onto what that means a little bit later on, but you can see it with inside one company, site to site. So a perfect example of that is Amazon, where we have the global backbone. And so you'll have an huge internal BGP network, and we peer across the different regions to advertise across different routes between the regions. At that peering location between the different sites, we then start to control, and I'll talk very briefly on how you can control those kind of things, but that's a whole separate talk. You've then also got the potentials to use it in your internal data centers. So an example of what I've seen before, I believe, is a leaf having its own AS number, and I'll get onto what AS numbers mean later. But that leaf having its own AS number, and then peering potentially with a spine, which has its own separate AS number, and then that connection between the two, we can control at a granular level to say, only let the leaf know about these specific prefixes. Now, if we look to the likes of MPLS, OSPF, ISIS, those protocols don't give you the same level of control, the same granular control as you do with BGP. And then there's also the generic company-to-company communication as well. So that is what the wider internet is. It is effectively just a web of connections between different companies. Everyone following along okay so far? All good? Cool. So some fundamental concepts, and hopefully I don't go too deep in this discussion where I kind of lose people, but hopefully you guys can keep along. I try to keep it as high level as possible. So to start off with, there is the fundamental block of a AS number. So what that stands for is autonomous system. And usually they're assigned to like a single company or a single region within inside that company, or in general for a autonomous system. And what we mean by that is a logical grouping of devices and networks, basically. So there are two ways that usually that is done. Is as I said, single company. So the likes of Exponentially, for example, or Discovery will have a single AS number for their whole network. And when they go onto their external connectivity, they peer with that AS number. Alternatively, a company can have a range of different AS numbers for different locations. A perfect example of this is Tata Communications. You may have heard of Tata, but Tata have a sub-branch of their business, which is communications and telecoms. And what they have is they have a global AS number, 6453, and they have a domestic number, which is 4755. And they have that domestic number because they are a mainly Indian company, and they have a lot of infrastructure providing like regional and domestic connections for Indian home broadband and those kind of things. So they logically separate their two networks, one which is a global transit provider, which provides internet routing for a range of different companies. And then also they separate out their domestic network, so they can control them separately, and they can be effectively two separate entities in the internet. Inside those autonomous system numbers, you also have a few ranges, but mainly two different ranges. You have a public and a private range. So the private ranges are between those numbers on the screen, 64512 and 65534 and 4.2 billion, I think, and the higher limit. We have two ranges because there's two sets of AS numbers. Originally, there was a 16-bit number, the standard specified as the 16-bit numbers, and later on, obviously, as the likes of IPv4 has been exhausted, we also needed to extend the AS numbers. So now we have the 32-bit AS numbers. And so inside both of those ranges, we have private ranges as well. So those private ranges can be used inside any network where we don't expect any external communication. So if you are inside your own internal data center and you're abstracted away from the internet by another peering to your actual AS number, you can use these private AS numbers to control your internal network. In theory, you could. There's nothing stopping you from using one of the public AS numbers inside your network. The only thing to note is obviously if you then start to connect into the internet, you'll start having issues because when it comes to configuration, the remote peers will accept a specific AS number, and they'll expect it to be your public one, for example. So that can cause some issues there if you don't do that properly. And so these AS numbers form actually quite an important building block for BGP, and it's the fundamental way that we actually route information around a BGP network, which is the AS path. Now, don't get me wrong, it's not the only metric that we use to decide the best path, and we'll get onto what that decision looks like a little bit later on. But the AS path is integral to the way the BGP works. Not only does it help to select the relevant best path, it also helps with loop prevention. And I'll talk about loop prevention on the next slide a little bit more. But in theory, what it says is that if you receive a prefix with the AS path that includes your own AS number, you're going to ignore it. And that's a very key fundamental inside BGP to prevent those loops. And then finally, there's the key, certainly when you're dealing with exams, the key detail that BGP is a path vector protocol. So comparing it to, as I mentioned earlier, OSPF is a link state protocol. It's link state because it knows about all of the links inside a network and those states alongside a bunch of other information, but generally routing is based on link states. However, inside BGP, it's mainly based on a path of a certain length or a certain vector from point A to point B. As I mentioned, there are multiple different attributes that we base path selection on, and I'll mention them a little bit later. But in general, BGP is a path vector protocol because it's based on fundamentally a path from A to B. Does that all make sense?
Yep.
I can only see Russell, so hopefully everyone's following along.
This brings me back to CCNA, I'll tell you.
Yeah,
Right.
I can imagine. So the flow of routing information. Now this is some key fundamentals here on how we advertise prefixes. And this all comes back to preventing loops. So to start off with, we have two versions, as I mentioned. We have eBGP and we have iBGP. So eBGP is the external version, external border gateway protocol. And that is used when we're peering with different AS numbers or different ASNs. So if we look at the diagram, for example, let me just make sure that you can see my pen. We have this little topology here, extracted from that bigger diagram that I showed a little bit earlier on the previous slide. Let's say AS3 advertises this, this prefix. When it advertises it to AS4, that's an eBGP peering. And that's okay, because we can advertise our iBGP learned routes to eBGP peers. So this prefix here would have been learned from probably redistribution from OSPF or another internal gateway protocol, IGP, to probably this device, let's say. This device probably has an internal BGP peering with this device. And I'm saying probably because obviously I haven't drawn it on, but let's imagine that is the case. So in this case, this device can advertise that on because it's just a redistribution into BGP protocol here. But when this device sees it, it knows that it can advertise it on to its eBGP neighbor because it knows that rule that we can advertise iBGP learned routes to eBGP peers. And we know it's an eBGP peer because of the different AS number when we have our neighborship. And that's one of the big attributes that we have when we actually set up these connections. We need to know the AS numbers. So then when AS4, or this device specifically, learns this prefix, it knows that it can advertise it on because we can advertise eBGP learned prefixes to an eBGP peer. So that advertisement is allowed. However, this device, and this is in general across BGP, not just eBGP or iBGP, cannot advertise back across the peering that it's just learned from the prefixes that it's just learned. And obviously that's the same in OSPF. You know, the route calculation wouldn't consider something that it just learned from the originating path, basically. So then when we look at internal BGP, there's another rule as well, is that we can advertise from eBGP peers. So let's say AS4 has now advertised to this device for this prefix here. This device can advertise it onto this device here. And that's fine because it's an eBGP learned prefix advertising to an iBGP peer, internal peer. However, this device by default cannot advertise it, this route that we've learned from AS4, onto any other internal peers by default. There is a way to get around this with route reflection, but by default that isn't permitted. And that yet again comes back down to loop prevention. If we start allowing that, then what's to say that we can advertise it there, then back there, then back there, and then back there, and then we start getting in a loop. And when you start to look at the actual path, so the AS path is the only thing that we know that we use to actually dictate where is this actually heading, where is it actually going effectively. And so if we don't have this rule internally that we cannot advertise iBGP learned routes to another iBGP peer, we lose that path and we don't know where it's been learned from. Now this is where route reflection comes into play, because there's a whole other set of attributes that we can use to track that that state, but that's a whole different topic as well. Does that all make sense to everyone? A little bit of word chamber.
Yeah.
Yep. Cool. Awesome. So very quickly, BGP control. How do we actually control the protocol? Well, BGP is based on TCP. It uses port 179 to control using TCP. And so BGP works at effectively layer 5, layer 4 being TCP, layer 3 being IP. The reason why it uses TCP is to ensure that there's no added complexity for reliability built into the protocol. And by that, it can keep the protocol, the BGP protocol, relatively simple, so that it doesn't need to stress about whether a remote device has received its message or not. If it hasn't, TCP takes control and resends the message till the remote device receives. Because of that, we don't have high bandwidth overhead on update messages. If we look back to the likes of OSPF, when we have a neighborship established I think it's every 30 seconds off the top of my head, you have to refresh the whole what's called an LSDB, link state database. And that database contains all of the information about the whole OSPF topology. 30 seconds might be the wrong time. I can't remember off the top of my head, but there is definitely a refresh of all of that information. And while it's only a summary, if you think of that summary, but then add in 840,000 prefixes, that's a lot of information to be refreshing every 30 seconds, let's say. And one thing that you've also got to consider is that 840,000 prefixes, that comes from one peer. So if I just take us back to this diagram here, if these are two transit providers and they have a full table and they're advertising it to us, let's take this device here. This device will have 2 copies of that full internet table stored in one of its memory banks to consider routes coming internally from this peering, and one to consider routes coming internally from this peering. That's why when we look at these kind of BGP devices, they're usually big, beefy devices that need to have big chunks of memory assigned to storing routing information bases, like BGP. So yeah, that's why we have TCP there, to control that flow of information and make sure that what we send is actually there. And that comes into also the protocol itself. So because we don't refresh and because we use TCP, we can assume whatever is sent and it's received and it's understood. So BGP doesn't need to resend details all the time of advertised prefixes. However, if something changes about that prefix, then that is the only time when we send a new update message or a notification. So in BGP, if everything stays exactly the same as it was when everything was set up, and you don't touch anything for 10 years, there would never be any BGP messages other than the keeper lives, just to ensure that the neighborship sessions exist. So there's that big concept there. Also, on top of that, when we actually send those messages to advertise the prefixes, we actually combine multiple prefixes with inside one single update where we have matching attributes. And I'll get on to what I mean by attributes later, but attributes effectively are the details of the prefix. So whether it's X AS path long, whether it has a certain weight, whether we have certain tags against it, those kind of things. And I'll get on to what I mean by attributes a little bit later. Does that make sense so far? Yep. All good? Yep, cool. So session establishment. I won't go into this too much, but there are some key things to remember. BGP versions must match. I don't think there's too many different versions of BGP, but they must match. The source IP address on the open message sent to the remote device. So the open message contains a bunch of different attributes of the session. That open message must match what IP address is configured on the local device. So when you configure BGP, you'll set a bunch of settings. You'll set the local AS number, the remote AS number, the remote IP, and in theory, you should set your local IP as well. So when you receive that open message with the source IP address of the sending BGP router, that must match the IP address that is actually configured on that device that is receiving it. The AS number also should match what is configured for the neighbor, and the router IDs must be unique. If it doesn't exist, if they aren't unique, then we don't form the session, because router IDs are used later on in the path selection as a tiebreaker. And so if you have identical router IDs, that can break some things. And then finally, you've got the security parameters that need to match. Cool. So path attributes, as I mentioned, we've got a range of path attributes that can help to describe the actual prefix that we're advertising. But also these path attributes, or at least some of them, factor into then the best path selection. So just to run through a few of these, we've got, and to be clear, this isn't like a full list. This is a top 10, let's say, kind of more well-known attributes that you would probably 9 times out of 10 see used. So there's origin. The origin is basically how it was put into BGP, whether it was learned from from IGP, so whether that's OSPF, ISIS, or one of those other protocols, whether it's from EGP. So back in the day, there used to be external gateway protocols other than BGP. Nowadays, it is mainly just BGP. So that E value you're not usually seeing. And then there's also incomplete. And if I remember correctly, incomplete is for when you redistribute. No, I don't think it's when you redistribute. I think it's when you have static routes that you redistribute. The static routes can be considered as incomplete when you see the origin code. You then also have the AS path, which I've mentioned. It's basically the path of ASs that you go through to get to the destination. You have the next hop, so that is identifying the IP address towards which the receiving device should send traffic towards for that destination prefix. You've got a multi-exit discriminator, or what we shorten to MED. And that MED value is, if I just go back to one of the previous slides, that MED value helps us in the case of AS2, if we've received a prefix from AS3 over these two links, it helps AS2 determine which two of the links it should send traffic towards AS3 on. So it's a way for AS3 to control the way that another AS sends traffic to it. Now, MED is only useful, though, if you have more than one peering session, 2 or more, with a single AS number. If it's just one device, if it's just one AS, then that MED isn't actually passed on to the advertising ASs. So if we advertise here a MED of 50 and a MED of 20 here, this will be kept internally inside this network, but that value won't be advertised on to any other ASs. That's just the way that MED works. We then have local preference. Local preference is just a locally significant attribute, which allows us to basically define locally how we want to prefer certain paths. So we can set some certain paths internally in our own internal network to say, okay, use this one or use this one. And local preference is the preferred way to do that. However, as we'll see with the path selection, that's one of the first attributes that we use. So if your peer is using MED, for example, or even AS path to alter how they receive traffic, your setting of local preference would overrule everything. And that's a key thing to remember. We then got a thing called atomic aggregate that basically identifies when someone has summarized a route and it just flags it up. With that, then you have to use the aggregator attribute just to identify the router ID and the AS number of who has done that summarization. So you can go back to that and expect the the actual unique prefixes. We then have a thing called communities. So these communities are kind of like tags for prefixes. So what we can do is we can tag certain prefixes with certain communities, and we can then use those communities to perform administrative control. And so that administrative control could be just blocking the advertisements of those routes with those tagged communities. It could be altering any one of these attributes. It really does depend on what you want to do, but communities are pretty flexible. And when you actually come to configure them, the community is usually just a numerical value, but in configuration, what you can do is you can map that numerical value to a real life string, just words, and then be able to reference those words in some kind of policy to say, okay, this is received from my customers. I want to raise the local preference of customer routes, for example. And then the final two are used for when we have route reflection. So we have an originator ID, which identifies the first internal device that is a route reflector that is reflecting that prefix. And then we also have a cluster list, which lists the route reflectors that have seen that prefix. That's how we identify the path internally. Yet again, route reflection is a whole separate topic. And finally, we have the best path selection. So that is based on a list of attributes, and they're what we've mentioned previously. We can use communities, as I mentioned, to prefer a certain subset of routes. However, this all comes down to altering the attributes that we have with inside a prefix to influence that route selection. So as I mentioned, increase the local preference for all prefixes tagged with the community high local preference to give to the given path, to the given prefixes. So to run through the path selection, we have weight at the start. Weight is a Cisco proprietary value. I don't know exactly why they have it, because we have local preference. I think just Cisco wanted to be Cisco and do their own thing. We have then local preference, higher is better. Self-originated. I believe that is where you have redistributed into BGP yourself. I think that is where that is used, but I could be wrong, don't quote me. We then have AS path, which I've mentioned. Shorter is preferred because that suggests a shorter path, shorter distance to get to the destination. We then have origin, which is, as I mentioned, how the prefix was advertised into the network, into the BGP network, sorry. We then have med, number 6, which is we prefer a lower med value over a higher med value. We then prefer an external eBGP learned route over an iBGP route, because obviously we trust eBGP to have no loops versus iBGP, where you might have some loops with the route reflection. It can get a little bit messy sometimes. And then we have IGP cost. So what we do there at that point is then we start to look at the next hop attribute that we have. We then do a normal route lookup, IP lookup to that next hop IP, and we identify which one has the lower IGP cost. And then we choose that route. Now at this point, if we are using something like multi-path, where we can ECMP equal cost multipath across a network, we stop at this point and we just load balance across the available paths that have matched up until that point. If we don't do that, we then get onto some tiebreakers, and as you can tell, they're a little bit arbitrary. So we've got the route age, so that's how long we've learned about the route, how long it's been in our routing table without a change. We then have router ID, so the router ID of the router that has just advertised us the prefix, and that yet again explains why we need the router ID to be unique. We then have the neighbor IP to really do a quick tiebreak between the two different routes. So it should be a lower neighbor IP, I believe. Does that all make sense to everyone? I can go into a little bit more detail if anyone needs it. Yes, a higher age is preferred. So that suggests more stability in the prefix that you've received in that direction. Okay. Any other questions? Everyone else following along? I think, if I'm not mistaken, that is it. So if you have any questions, I think this is a good point to ask them.